right, here we go. Lecture number 4 for 9.7. Like I said, these last two sections are kind of intense and just a lot of information to absorb. So that's why we're kind of spreading it out over the course of the week here and get our good introduction before that test comes. So this is lecture number 4. We finished up with the idea that you can use E0 of the cell. A positive one means you can make a battery out of it. It's thermodynamically favored. It is possible to combine them so that they would have an E0 value of less than 1. And this, we just finished up our previous lecture with. This is kind of a confusing idea, because if you always take the smaller of the two numbers and flip the sign, that will always be positive, and that's a true statement. However, if you look at the way that the reaction occurs, you have to look at what are the reactants and what are the products, and then use that to determine whether it's an oxidation, reduction, or whether it's reduction or oxidation. So that's what this is kind of looking at. Like, for instance, you have this reaction. All other things being equal, you would look at this data and you'd say that one's smaller. I'll flip the sign and it's going to be positive. But as you can see down here, the answer is negative. And that's because you're given what the substances are. The bottom line is you start with solid lead. Okay? Now, solid lead is not going to react non-spontaneously, and it won't be thermodynamically favored if you put it in with barium sulfate. And here's the reason why. Because this reaction right here is not what's happening here, is it? Because it's starting with solid. So this is the flip of this, and then it goes into being a +2 ion. So this one has to be flipped. So because of the way the reaction is written, this is your oxidation. Okay? And as poor as this is what's happening. This is what you were given in the beaker. You had barium +2, is exactly what we have here. +2 electrons give you solid barium. So this is happening in the reaction. So we don't get to change this number because this is reduction. It shows it in the chemical reaction. So that is a case where you'd have a non-thermodynamically favored process. It's negative quite a bit. So that's not going to be a very good battery. It's like sucking power from the universe. But if you wanted to do this, let's say you wanted to get solid barium for some reason. You wanted to use lead and barium sulfate to drive this. You could hook it up and power it to drive that non-thermodynamically favored process. Okay? So now we're going to get into relating delta G to E0. Okay? So we can see here that there's a nice little equation where your delta G at standard conditions in joules per mole again. So you got to be careful with these units. Always check the units whenever you're working. If we're doing the one with the summation and adding up the things and looking up the values of all the delta G's, it's almost always kilojoules. But in this case, is another example of where you'd want to use joules instead of kilojoules. And then N is the number of moles of electrons. I think this is the trickiest part of this. You got to be careful to figure that out correctly. How many electrons are transferred. That previous example where we had to double the aluminum and then it didn't change the standard reduction potential, but you got to kind of be careful about that. Now, this is a Faraday's constant, 96,500 coulombs per mole of electrons. That's a constant, okay? That's why they call it Faraday's constant. That's not going to change. I'm disappointed we didn't get to do a pretty cool lab where we take 2 pieces of copper. So you're making a battery with copper and copper. And in order to do that, it's not a battery. So that's electrolysis, which is we're getting into. You have to plug it in to drive it uphill. Okay. So as delta G becomes more negative, circle this on the bottom here. This is a good thing to kind of get down. Is to know that as delta G is more negative, that's more spontaneous, more thermodynamically favored, and the E0 becomes more positive, and you got a better battery. And as delta G becomes more positive, that's not so good for your battery, and the E0 actually becomes negative. So there's a real relationship to those, and that's why you need that negative symbol in there, because they're opposite in how they do this. Okay, now this problem says find delta G and the equilibrium constant Kc. Oh, this is interesting. Now we're throwing in equilibrium constant and delta G and being given standard reduction potentials. So talk about tying all of our stuff together into one problem. This is a pretty good lecture to save for the very end, because if we didn't, we were just talking, let's start talking about electrochemistry, you'd be going, what's delta G, what's Kc? But you're not saying that. So anyway, here's our reaction, and here are the values. Now notice we ignored the 3 out front there, at least for now, because it doesn't matter. You could put them in there in that equation, but right now they normally just ignore the coefficients, the 3's and the 2's, in setting this up. And certainly, if you look at this in balancing this, it's just manganese and chromium give you manganese and chromium. You could put any numbers you want in there as long as the ones on the manganese were the same and the ones on the chromium were the same. So again, what you're going to be doing is balancing charges with that reaction. But here are our reduction potentials. So it says we want to find delta G and the equilibrium constant. So the first thing we're going to do is find delta G using the new equation that we just talked about, by getting the E0 for this process. So E0 red plus E0 ox, and then you have to look at the way the equation is written. It goes solid manganese to Mn plus 2. So that's not this one, so you have to flip this guy. So when you flip that, you're going to get the plus 1/8, okay? And when you look at the chromium, it goes from plus 3 to solid, which is exactly what this is, so you don't flip it. So you can see right now the E0 is going to be positive. So this is going to be a spontaneous reaction. So how do we go about doing the rest of that? So E0 red plus E0 ox, that's always the easiest way to do it. And you got to be careful. We need to use the equation, because maybe we would have flipped this one, depending on the way that that equation was set up, okay? So bottom line is we end up with an E0 that is positive. Now, that means it's thermodynamically favored. Now we move on to this right here. Now this is important. You have to realize what's happening. when you have two chromiums going to two solid chromiums, and there are 3 plus charges, it's going to take 6 electrons in order to do that. Okay? So remember, this is gaining electrons. 2 of them have to gain 6 electrons in order to lose all their charge. So this one's losing. How many does it have to lose for 3 manganese to gain a +2 charge? It's got to lose 2, 4, 6 electrons. So now you have 6 electrons gained and 6 electrons lost. So that is why the equation was written that way, and that is the electron number, or N, that we use in this equation. Kind of unfortunate that they use that lowercase n for a lot of things, but you could think of it as being moles of electrons, and n is moles. So so there's your n is 6 moles of electrons, and this is 96,500. That's the constant that is never going to change. So you just look back and at the equation here, Faraday's constant, and that's on your purple sheet. That's always going to be the same thing. All right. So now you're just plugging that in, and you get delta G is a negative 250,000 joules per mole. And we went with the 2 sig figs because of that number right there, of course. And then, as we know, delta G is usually expressed in the end in kilojoules per mole, because there's usually so many of them if you do joules. So either one of those answers would be acceptable, unless they said how many energy, or what's the energy, or delta G in kilojoules. You'd have to obviously make sure you do this last step. But this is really commonly done because it just sort of makes a little more sense. You get a more manageable number that way. Okay, so that was a great application of using delta G and delta F, but we haven't finished the problem yet, because if you'll remember, go back to the question, it says give delta G and the equilibrium constant, Kc. So how are we going to do that? Well, delta G equals minus RT ln Kc. You take the natural log of both sides. There's your delta G value. Remember, you got to use this special R value, not the 0.081, but 8.314 joules per mole Kelvin. And if you write the units down, that helps you remember that. But of course, that's always optional in the setups. And then you want to get rid of the natural log, so you take E of everything on the right, so raise E to this as a fraction. And again, I strongly recommend punching that in your calculator and using so do this before we move on to the next lecture. We're going to stop on this problem actually. So Kc equals 6.6 times 10 to the 43rd, no unit, and very, very much favors a reaction to the right. So all those things agree. We had a positive delta E. That means it's going to happen spontaneously. Kc means there's going to be lots of products, and a negative delta G, and actually fairly large negative delta G, means that you're going to really strongly favor a thermodynamically favored process. So that just tells you this would be a good battery. Okay, so this is the end of lecture 4. We'll see you on lecture 5.